All right, everybody, we have talked about the force of gravity. We have talked about work. We have talked about changes in kinetic energy. And we're going to put that all together today to talk about gravitational potential energy. So real quick, we're going to talk about potential energies in general because there are a couple of different kinds of potential energy. We are going to talk about most of them this year, but first, of course, we'll talk about gravitational potential energy. So in general, potential energy is energy that is stored between two objects in a system based on the configuration of the system. So how far apart are the two objects, where are they located relative to each other? And this occurs because of internal forces. So some examples of two object systems that can store potential energy. We might have a ball earth system. We might have a block and spring system. We might have an electron and a proton system. Okay? All of these things are two objects, and they're all going to store energy because of their configuration and because of internal forces. Okay? So we can have potential energy at the microscopic level, and we're going to talk more about this when we talk about phase change. But this is potential energy that is due to the distance between two particles. Okay. So when we calculate the potential energy at that microscopic level, the potential energy is actually equal to the negative of the inverse of the distance between the two objects. So what this means is as we increase r, the distance between the two objects, we're going to increase the potential energy. Okay, so if I was to graph potential energy versus R, and again, this is microscopic, the graph actually looks something like this, right? So if I have a very small r, that means I have a very negative potential energy. Now, the negative here is truly a negative number. It's not like force or velocity where negative means direction. So the magnitude of this potential energy is very small. Whereas if I have a very large distance, I notice that the potential energy is less negative. So the magnitude of the potential energy has increased. Right? So that's microscopic. Right? This is why it takes energy to go from a liquid to a gas without a change in temperature, right? So this is why there's those flat parts on a phase change diagram. During this flat part, the temperature is not changing, the kinetic energy is not changing, but the potential energy is changing. What we're doing is we're working to break some bonds and pull those particles apart, giving us more potential energy in our system. So then we have macroscopic potential energy, and macroscopic potential energy, no matter what kind we're doing, is also going to increase with increasing distance between. We don't have to deal with a negative here, luckily, but even at the large scale, as we increase the distance between two objects, we're going to increase the potential energy within the two object system. So we have three major kinds of potential energy. We have electric potential energy, which we could represent with a UE. This is energy stored in an electric field. Okay. Now here's a fun fact. Oops. The units for an electric field are a Newton per coulomb. So they tell us the amount of newtons or force a charge feels. C is the unit for charge. Coulombs is the unit for charge. We got gravitational potential energy, U with a subscript little g. This is energy stored in a gravitational field, and we know the units for gravitational fields are newtons per kilogram. And then we have U with a subscript of S, which is elastic or spring potential energy. And this is energy stored in a spring or elastic device. And we actually determine how stretchy or not stretchy a spring or elastic device is with something called a spring constant. And that spring constant has units of newtons per meter. So you maybe notice a pattern here that all of our potential energies are going to end up tying back to forces. right? But depending upon what we're talking about, the force per, is it the force per coulomb, force per kilogram, force per Newton? That's going to change the kind of potential energy we're talking about. Just a fun pattern I wanted to throw out. So we'll talk about each of these as the year goes on. Electric we'll talk about when we get to phase change. Spring we'll talk about in a little bit. But today we're talking about gravitational potential energy. So this is energy stored in an object Earth system. There is a, what I like to call planet-sized gravitational potential energy, which of course is energy stored between, say, the sun and Jupiter, or the Earth and the moon. But for now we're talking about objects on Earth, so we'll talk about the energy stored in an object Earth system. Due to the interaction between the Earth's gravitational field, so we're going to be dealing with a little g, and the object's mass. Okay, this is based on the height of the object relative to some height equals 0. So the height might not necessarily be above the ground. It might be a height relative to the ground or the table or maybe even a ceiling. We're going to pick what a height of 0 is based on the context of the question because we want a nice convenient height of 0, right? So usually we'll set our lowest point to our system to be a height of 0 because we can have a negative height if the h is below 0. Okay. Potential energies can be negative, but remember kinetic energy cannot. Okay. So let's talk about deriving the equation. Okay. Now, in general, this is just a rule in physics, is that work done by internal forces can actually equal the negative change in potential energy. That's going to be true for all of our potential energies, whether it's gravitational, whether it's electric, and so on. So if I can figure out the work done by a force of gravity on, say, a ball-only system, then I should also be able to figure out, okay, what would be the change in gravitational potential energy of the ball Earth system. Okay, so we talk about the work done by the force of gravity because that is the force that becomes internal in the ball Earth system, and that is the reason why we can store that potential energy. So I should be able to derive an equation for gravitational potential energy by looking at the work done by the force of gravity on a ball-only system. Okay. So let's say I have a ball that is released from rest, and that ball falls a distance h to the ground. Okay. So I want to figure out the work done by the force of gravity, and I know the work done by any single force is the value of that force times the value of the displacement times the cosine of the angle between them. So the force here is just the force of gravity. The displacement here is h. And let's see, my force of gravity is going to be down. And I am displacing down, so that's a cosine of 0. So force of gravity is mg h. So the work done by the force of gravity is going to equal mgh. Okay, so now the work done by that force of gravity is going to equal negative the change in potential energy. So really the change in potential energy of this ball Earth system is going to be a negative mgh. The negative meaning that we have decreased in potential energy. Okay. So if I think about this, my ball was at a height above the ground, and now I am at a height closer to the ground, and we'll say the ground is h equals 0. So I have decreased in height. I have decreased the distance between the ball and the Earth, so it makes sense that my potential energy should decrease. Okay. So we say that we can calculate any potential energy by doing mgh. And what we usually actually do is we usually calculate a change in potential energy. So it's really an mg change in height, where again, g is that gravitational field strength of 10, m is the mass, and h is the change in height. Okay. So that's our equation for UG. A bunch of direct relationships in there, which is really nice because that makes some comparisons nice and easy. Okay. All right. So the force of gravity is considered to be a conservative force. And what that means is that any changes in potential energy are path independent. Okay, we have a couple of forces that are conservative forces, which means they are path independent, or changes in their potential energies are path independent. I'll give you some more examples here. Okay, but for now, let's talk about potential energy. So let's say here's West Mountain. Clearly, this is a mountain. Okay. And let's say on the first day, I hike up West Mountain and I do a bunch of switchbacks, right? But I still go from the bottom here to the top here, right? So let's say that's day 1, we'll call that path A. Day 2, I still want to go to the top. I still want to see the view, but because of all of my hiking yesterday, I'm very sore. So I now pay the however much money, and instead of hiking all the way up, I now take the chairlift all the way up. Okay, so there's B. So think for a second. I would like you to compare the change in gravitational potential energy of day A and the change in gravitational potential energy of day B. Okay. So pause the video and think for a second, right? Thinking back to how we calculate change in potential energy, how do we think those compare? Now, potential energy is calculated with mass, gravitational field, and a change in height. My mass is the same both days, and I am on Earth both days, so the gravitational field is the same. So the m and the g are the same. So I just have to compare the changes in height. Now, both days I start here and I end here. So my change in height looks something like that. And no matter whether I'm doing the switchbacks or going up the chairlift, my change in height is the same, which means my change in potential energy is the same both days. So that's what we mean when we say the change in potential energy is path independent. Okay. This also means that if I was just considering me instead of the me-Earth system, the work done by the force of gravity would be the same each day because force of gravity is conservative, meaning that D in the work equation really means displacement. Okay. So, path independent. Doesn't matter how I get there, just that I got there. So some other conservative forces, we are going to have our spring force, Fs, Hooke's law, which we've talked about, and our electrostatic force. Right, so the other forces that are governing our other potential energies, right, our UE and our US, those are also conservative forces. So some non-conservative forces, some forces that will change our energy depending upon the path we take. Those are going to be things like friction, applied forces, things like that, right? Now, if I was to consider the work done by friction on my first day and the work done against friction on my second day. Now let's say the second day, instead of taking the chairlift, I just hike straight up the mountain, right? Now if I think about A, my path is very, very, very long. So I'm experiencing friction over a very large distance, especially compared to A. And because friction is not conservative, the D in that equation really means distance instead of displacement like it does for conservative forces. So for day A, the work done by friction is going to be much larger. That's why for A, I might feel a little bit more tired or worn out. Okay. All right. So let's talk about tracking our energy. Okay. So we talked about the ball system versus the ball earth system. We talked about it in terms of equations. So let's talk about now in terms of like a visual. Why does how we define the system matter? So let's again say that we are dealing with a ball that is dropped, a height h to the ground, and that's where our height is 0. Okay. So if we consider the ball-only system, the force of gravity is external to that system because it is between the ball and the earth. The earth is external to that ball-only system, which means the force of gravity can do work. That also means the only kind of energy this ball can have is kinetic energy. Okay. So if I was to kind of diagram this with like a before, what happens during, and the final, it might look something like this. So these, we're going to draw bars to represent energy or work. So before the ball is dropped, I have a speed of 0. No work has been done on the ball system. So we're really starting with 0 kinetic energy. Okay. During the fall, the force of gravity is going to do positive work because it is in the same direction of the displacement. So during, we're going to have work done by the force of gravity. Okay. And we know that work done by external forces can change the kinetic energy of the system. So all of that work done by the force of gravity goes into increasing my kinetic energy. Okay. So that's how we would have approached this system for today. So now if we have the ball earth system, okay, the force of gravity is now internal, so we can store gravitational potential energy. So when I'm considering the mechanical energy of the system, this system is capable of kinetic energy and potential energy. Mechanical energy is our potential energies plus our kinetic energies. We can think of this as like usable, reusable, retrievable energy. Now our mechanical energy might change based on how our system is defined. For instance, for the ball only, we had only kinetic energy, but now we're in the ball earth, so we can have kinetic and potential. Okay. So I can again think about my before, my during, and my after, or my final. Okay. So before, I had no kinetic energy because I was not moving. But now I have, because I'm at a height relative to the earth, I now have some stored potential energy. Now, force of gravity is now internal, and that's the only force acting. So my external work is 0. Okay. But I still end up with kinetic energy. So in this system, instead of the kinetic energy coming from work done, my kinetic energy comes from energy I stored in the system. And there are different benefits to why we would define our system as the ball only and the ball earth system. Here in the ball earth system, this is a convenient way to define this system, because in this system we could say mechanical energy is conserved. Okay? Meaning I started with 3 bars of potential. No work was done to change my energy, so I could end with 3 bars of kinetic. We're going to talk more about energy conservation later, but just as a tidbit now, right? So it's not like any of the heights of the bars are changing. We're just kind of changing where are we saying that kinetic energy is coming from? Is it coming from work done by the force of gravity in the ball only system? Or is it coming from stored energy in the ball earth system? Okay, same amount of energy, same result. We're just looking at it from a different lens, kind of like we did with our multi-object systems, right? We changed our system depending upon what we were looking for. And as we changed our system, our free body diagram and net force equation changed. Similar here. So where does gravitational potential energy come from, right? Like we have this before, we know it started with potential energy, but where did it come from? Okay? So our potential energy, of course, has to come from somewhere. Energy is not just simply created. It doesn't simply disappear. It has to come from somewhere. We have to be able to say where it comes from. So to increase the potential energy of a system, we either need work done by some external force or object that increases that potential energy, or it can come from some other energy in the system. Okay. So I'll give two examples. Okay. So here's an example of where our potential energy would come from work done by an external force. Okay. So let's say we have a box. Here's my H equals 0. This is the box Earth system, so I can store potential energy. So the box is initially on the floor, and then the person lifts it, and it is now at a height h. Okay. So initially, my box had 0 kinetic energy, 0 potential energy. And up here, if it's at rest, it has some potential energy. So we got to figure out, all right, where did that potential energy come from? Well, I said the person lifted the box. So that must mean that the person did some work because they applied an external force. So that work done by that person is what caused a change in potential energy. Right? Energy always has to come from somewhere. So an example of where we could get some potential energy from, say, a kinetic energy. Again, let's say we have a box Earth system. Let's say we have a box that is traveling across a surface at a speed v, so we have some kinetic energy here. And then that box slides up this incline, let's say it's frictionless, and reaches some maximum height. Okay. So initially there was kinetic energy, and then here, when we're at rest, right, we have stored potential energy in the box Earth system. So where did this potential energy come from? Well, it came from kinetic energy converting to potential energy. Okay. Now, if the system is frictionless, the initial kinetic and final potential should be equal. If there is friction, we're going to lose some energy along the way, so the initial kinetic should be slightly larger. Again, we'll talk more about that energy conservation as we go through. So, why do we care about potential energies in general, or specifically gravitational potential energy? Well, we like to be able to store energy because we like to be able to do stuff with it, right? That's why batteries are really great, because we can store energy and then do stuff with it. So a lot of times we talk about gravitational potential energy as a way to speed objects up or maybe slow objects down, right? So we want to be able to turn it into other kinds of potential energy. So this is going to dive a little bit into energy conservation, but it'll help us as we kind of move forward into the next bit. But this is what we're going to end up doing with this gravitational potential energy, because looking back at our equation, like, that's a pretty boring equation, right? There's not many questions I could ask you that are too complicated. So really, what do we do with that potential energy? So here's what we're going to do with that potential energy. We're going to do some energy conservation. Okay. So if the net external force is 0 on our system, right, our likely object Earth system, then that means our work done by any external forces is 0. Now again, that's not saying that there are no forces. There certainly could be a normal force or an applied force, but it's saying that those forces, if they exist, do not do any work. So they are perpendicular to our displacement. So what that means is our mechanical energy is conserved. Okay. So mechanical energy is the sum of all of our potentials and kinetic energies. It is not our Q or our heat. Okay? Mechanical energy is usable, retrievable, right? Once we lose energy due to heat, it's really tough to get back. Okay? So remember, be careful how our system is defined. That'll really determine what potential energies we have, right? That'll also determine if there are external forces that do work. But let's say we've defined our system in such a way that there are no external forces and that our mechanical energy is defined in such a way that it is conserved, right? So conserved means constant or remains the same. So that means whatever initial energy I have, that's going to equal whatever final energy I have. So that means the sum of my potential and kinetic energies at whatever initial point I have. It could be the top of a ramp, bottom of a ramp. It could be the top of a roller coaster loop. It's obviously very many positions, right? But that initial has to equal the finals. And I'm saying U and not UG specifically because this potential could also include spring if we're including a spring in our system, right? So we're going to end up using gravitational potential energy to deal with energy conservation problems. And then we'll add in, of course, what happens if there is work done on the system. If there is friction, we'll use potential energy there too. Okay. All right. So for now, quick recap, gravitational potential energy. Energy stored in an object or system due to the interaction between gravitational field and object's mass. It's based on the height of the object relative to some zero, and it can be negative if the height is below a height of 0. It essentially means we've lost potential energy relative to h equals 0. Okay? So we are in the object Earth system, right? If we just define our system as the object, we can't store potential energy because potential energy needs to be stored in two object systems. Our equation for gravitational potential energy is mgh. We should add that to our energy section on our reference table, and that comes from calculating the work done by the force of gravity. Okay? As we know that the work done by any internal forces is equal to the negative change in potential energy. Okay? So as this ball fell, it lost potential energy, which makes sense why it had a negative mgh, because we had a decrease in potential energy. So we also talked about how the force of gravity is considered to be conservative force, right? The big thing there is that potential energy is path independent. So what that means, again, in a nice simple way, is let's say I can either lift a box or I can push a box up an incline, but either way, the change in height of the box is the same. So whether we're dealing with situation A or scenario B, where I'm going up an incline or I'm lifting the box, my change in potential energy in either way is the same, because all I care about for potential energy is this height. I don't care how I got to the height. Okay. All right. And then we talked about, all right, what does it look like if we change our system? How does the ball system only compare to the ball Earth system? Okay. For a falling object. So really what it changes is, do we have work done by gravity or are we storing potential energy? Okay? You will never have a situation where there's work done by gravity and stored potential energy. It's one or the other. Can't have both. And that's gravitational potential energy.